Okay, guys, welcome to some notes over chapter 17. So this is the last section on equilibrium. We've kind of added this part of thermodynamics to our equilibrium notes due to the fact that free energy and the equilibrium constant expression kind of go hand in hand, and I'm going to try to get through explanation as to why. And I'm going to move a little faster in this video than I have in the past. I'm going to go through the example problems a little more quickly because I just don't have that much time. But if you have questions, ask your instructor and it'll be okay. So let's see if I can get this to work here. All right, so here we go. This should work. Hello, start broadcast. Okay. So there we go. So yeah, we're talking about entropy and free energy. For the most part, we're going to be talking about free energy or delta G. But spontaneity, entropy, and free energy are all kind of related. I will say though that spontaneity, the word spontaneous, it's not actually it's not a word that or a term that a College Board really wants you to use. What they really want you to use is thermodynamically favorable. So thermodynamically, if I can spell it right, favorable. Yeah. So that's what they want you to use instead of spontaneous. Spontaneous is okay though. If you were to write it on your exam as an explanation for what's happening, it's okay. Not a big deal, but that's kind of, like polarizable electrons versus saying it has a lot of electrons. Both would be acceptable, but one is more sought after, I suppose. So the first law of thermodynamics states that energy is not created nor is it destroyed. It's constant in the universe, but it can change. We can measure energy changes in chemical reactions to help kind of determine what's going on. So keep in mind that when we're talking about thermodynamics, we're talking about reactants and products both. We're talking about, in some cases, shifting towards the product side would be, a spontaneous reaction, while if it favors the reactant side, that would not be spontaneous. Kinetics, however, what we did prior to this, deals only with reactants disappearing and becoming products or product formation, either one. It means kind of the same thing. But it would be changing from reactants to products, not really concerned about the reverse reaction there or what's happening to them individually or together, I should say. But it's similar, but one is one direction, the other is kind of both. So spontaneous reactions, or those that are thermodynamically favorable, are ones that occur without any outside intervention. So, I mean, you might think that, oh, if you cause some hydrogen explode, you actually had to light a match. There is going to be a little activation energy for any reaction, but it's a very small amount of activation energy to get the reaction to occur. The reaction is certainly considered to be spontaneous, even though it may need small amount of activation energy. Ones that actually favor the reverse reaction or more reactant formation than product formation, or they form very little products, may not be spontaneous under certain conditions. It may be that it changes. If you change the conditions or you input energy, you can get it to happen. But that's the difference between spontaneous and non-spontaneous. So the picture here that we're looking at, this picture here is dry ice in water, probably in warm water. But when you drop it in there, it sublimes very quickly. It's a spontaneous process. It's changing from a solid to a gas immediately, no problem. And that's quick. That may be what you think of as spontaneous, but spontaneous doesn't have anything to do with the time. It just has to do with the energy. Does it have enough energy for that to occur? A slower one would be rust. So forming rust would be a slow, long process, but it is spontaneous. It doesn't happen with any outside intervention. So entropy is one of the terms that we'll use to describe what happens to certain systems. Some will decrease in entropy, but the majority of reactions actually increase entropy. Certainly, the universe is constantly increasing in entropy. And if you don't put energy into a system, generally speaking, the entropy level goes up. So if you don't clean your room turns into a disaster, right? And there's a couple of examples up there. We're looking at, a sock drawer here that's completely organized, which isn't quite what mine looks like, but mine is similar. to one that's, kind of all thrown in there. They're not even, paired up. That would be something that has high entropy. So entropy is actually a measurement of the disorder of a system. So your room may be highly entropic, so to speak, or it may have low entropy, meaning that it's quite ordered. This is fine, but it is a measurement of what happens in the chemical processes as well. There are some ways to increase entropy. Entropy is obviously increased when it goes from a solid to a liquid. You are increasing the temperature generally in order to do that phase change. So entropy also increases with increasing temperature. And also, if you look at the product side and you actually form more molecules or atoms versus what you started with, for example, decomposition of hydrogen peroxide, you have more things as products. That's also increasing the entropy. And so there's the same stuff just showing you if you produce more molecules or you phase change towards gases or you add temperature, add energy, you're actually going to increase that entropy level. There is a relationship between energy, here I'll leave it there, entropy and our actual free energy. So, and what free energy is going to tell you is whether or not a reaction is actually spontaneous, whether or not it's actually thermodynamically favored and will happen at a certain temperature. And there's calculations associated with it that we did last year in advanced chem, but you may have forgotten, of course. So the second law of thermodynamics says that the entropy of the universe is always increasing. It requires energy to keep that from happening. So, and we have already discussed that. Here's the formula that you use to calculate for whether or not a reaction would be spontaneous at a given temperature. So, and we had this last year, but it's a calculation of Gibbs free energy, which is delta G equals delta H minus T delta S. It's actually the Gibbs-Helmholtz equation, whatever. But you can calculate what delta G is. If delta G is negative, it means that there's more work than is necessary for a reaction to occur. And that reaction would in fact be spontaneous. If delta G is positive, then what happens is the reaction is not spontaneous and it needs additional energy in order to occur. So when delta H is negative, that's when delta H up here is negative, it's very likely that delta G is also going to be negative. So things that give off energy are generally spontaneous, but not always. It kind of depends on the temperature and it depends on what the entropy value is. So those letters up there, the delta G represents your free energy. Delta H we've already had represents your enthalpy or your heat, whether it's endo or exothermic. Your temperature is in kelvins, of course, because we can't have negative heat values. We can have loss of heat values. And then delta S will be your entropy value. I don't know why S is entropy and it's not like an E, but its entropy is delta S. So, yeah, one of the things that's kind of interesting here, and I'll hit on this again multiple times, but when things are in phase changes, like when ice melts, the delta G is actually 0. You can use that information to actually go calculate what the freezing point of water is, or the boiling point if you knew it as well. But during phase change, delta G values are 0. However, if we're not talking about a phase change and we wanted to kind of manipulate the equation to figure out whether it's spontaneous, when the signs, positive or negative, signs of S and H are different, then it's either going to be always spontaneous or not always, or always non-spontaneous. So there, if you look at here, I shouldn't have circled the whole thing, my apologies. So these two right here, if delta S is always positive, or if delta S is positive and delta H is negative, then the delta G resulting for that will always be negative. And so that means that if I kind of play with it, I don't need numbers, I can just look at the signs of the numbers. But if I have a negative here, and then I've got a minus sign, minus a positive, and the temperature is Kelvin, so it's always positive. A negative minus a positive, so negative minus a positive is always going to give me a negative value. That's why we say it's always going to be spontaneous. If the signs are different, it's going to be one or the other. Well, what if I had something that was positive? So I have positive H and a negative S. I have a positive minus a negative. That's always going to give you a positive value. And so those reactions that have enthalpic values, in other words, positive delta H, and they have decreasing entropy values, so negative delta S, you would actually see a reaction that is not spontaneous and would favor the reactants. If, however, they're different, if they are the same, the signs meaning they are the same, if you had a positive minus another positive, you don't really know what that is. It's dependent on what your temperature value is. If both signs are negative, once again, it is dependent on the temperature. And so you can play with it and see whether it's high temperature or low temperature for spontaneity to get a negative delta G value. But that's the way this kind of chart is set up in your notes. So the next thing that we're going to talk about is changes in entropy in different chemical reactions. The third law of thermodynamics basically says that enthalpy values are always going to be positive. That really is because doesn't mean a change in entropy is going to be positive, but every substance has a positive entropy value. There's always a probability of things getting more disordered. Also, the temperature is in kelvins. So the entropy of a perfect crystal or of a substance at zero is in fact zero entropy. It's the only time that you can have zero entropy is if you have absolutely no heat or energy associated with it. So any substance at 0K must have a value for entropy, or sorry, any substance that's not at 0K. So anything positive is going to have a value for entropy. Those values are actually very small. Entropy values are given in joules instead of kilojoules, which leads to some unit conversions, but they're actually quite small. So here's just a quick example. You're given an equation up here at the top, and you're going to calculate the change in entropy for the entire reaction. So it is done just like we did delta H or enthalpy calculations. It is the product values, the sum of the product values minus the sum of the reactant values. So if I circle my product values up here, I've got magnesium as a product and I have aluminum oxide as a product. I would add those two together, multiplying by their coefficients, and that would be the sum of my products down here at the bottom. And then the other two that I'm just underlining here are my reactants. I would take both those, multiply them times their coefficients, add them together, and subtract from the products the entire sum of the reactants. So if I set that up and solve, and you can hit pause and do these on your own if you would want, to be a good idea. Or if I move too fast, please don't hesitate to pause. But these calculations end up with joules per mole K, or joules per Kelvin mole. It does say joules per Kelvin mole reaction. It just means for the reaction above as written. But that is the change in delta S for that reaction. And that can be then used in subsequent equations to say solve for free energy, or to solve for the enthalpy value having been given free energy, and so forth. So free energy in chemical reactions, the standard free energy change, or the delta G of a total reaction or complete reaction, can be calculated the same way as the entropy values and enthalpy values. It's just products minus reactants. If you're given them, now they're going to be in a chart. Now what it means by standard here is this little naught symbol means that these substances are at 1 atmosphere of pressure, concentration of 1 molar if they're aqueous, and they're done at 25 degrees C. I know that STP is 0 degrees C in 1 atmosphere, but standard changes for enthalpy, entropy, and Gibbs free energies are going to actually be at 25 degrees C. But anyway, that's what the little naught symbol means. So these could be presented to you in a chart. You'd have to be told what they are. You could go calculate what the change is, but the actual individual delta G values, delta S values, or delta H values will be in the chart, and they'll have a naught symbol, meaning that they are standard. If something is by itself, and you might remember this from us doing, delta H calculations in our thermochem unit before Christmas, is that if it is a free element in its standard state. Now, free elements mean an element by itself. So sodium as a solid, as you would find it at 25 degrees C. Sodium as a solid, its value will be 0. If it is oxygen, which is a gas at 25 degrees C, it will have a value of 0. If it were oxygen liquid at 25 degrees C, it probably had, not monatomic, sorry, O2, a liquid at 25 degrees C, it will have an entropy value. It will have, well, they'll all have entropy values, but it will have a delta H and a delta G value. So you'll have to look and see what you're given on your chart, but know this, if you don't see it in the chart, it's very likely that you're either solving for it, as it's the only one missing, or its value is 0. So let's just do one example, and I'll kind of call it quits for this video. But given the equation in 204 is changing to 2 moles of nitrogen dioxide, calculate the delta G. Very simple. So you're going to take your product values minus your reactant values. Our product value or product or compound here, our product is actually NO2. So we would take the 5130, multiply it by 2, and then subtract from it our delta G for the reactant. So it would look like this: products minus reactants multiplied by their coefficient. The units for delta G are going to be kilojoules per mole. The units for delta S, remember, were joules per mole. So when we do calculations in Gibbs Helmholtz, we're actually going to have to do a little bit of converting. So we're going to call it kind of quits there, and I'll come back in a second video and finish up chapter 17 for you guys. If you have questions, remember, go talk to your instructor, and we'll see if we can help you out.